Today I would like to continue the discussion of electric and magnetic field and tell a little bit how we describe these fields and which vectors or variables we use to quantitatively describe this. As a reminder, I draw again. I will not draw source of the field, but I just draw the field lines. Let's assume we have electric field like this. We also have magnetic field like this. If you're not drawing the source of the field, which are charges for electric field and electric current for magnetic field, the lines, actually the electric field strength lines and magnetic flux density lines looks pretty much the same, so you never can find out what is what if there is no clear definition of it, where is E, where is B. First of all, what these vectors are, what is E and what is B? Let's start from electric field, and for electric field the vector E refers to electric field strength, which is measured in volts divided by meter. And for magnetic field, the vector B is magnetic flux density, or the vector of magnetic induction, which is measured in Tesla. This is actually a very important vector, very important field characteristics. That's why there is a special name of it, Tesla, but actually Tesla equals to Newton divided by ampere meter. Yeah, Newton divided by ampere by meter. This is actually Tesla. And we have also related vectors, related quantities to describe these fields. In addition to this vector E and vector B, they are vector D, which is the electric displacement vector, also usually or quite often referred to polarization vector, and vector H, which is the vector of magnetic field strength. The difference between these vectors is that one vector usually taking the medium into account or the material into account, another vector is not taking the material into account. The correlation between this vector is the following. Vector D equals to epsilon 0 E, where epsilon 0 is the constant and epsilon is the relative dielectric permeability of the material. So vector E is basically don't take the material into account, but vector D already taking the properties of the material. Vector H goes a little bit vice versa. Vector H equals to vector B divided by mu 0. Mu 0 is the constant and mu is the magnetic property, magnetic permeability of the material. So here we assume that vector H refers to external field strength, and it's usually officially named as magnetic field strength. And but vector B is the magnetic flux density in the material. And here in vector B, the characteristics of the material, which is mu, taken into account. The dimensions of electric displacement vector is Coulomb by square meter, and dimensions of magnetic field strength vector is ampere divided by meter. This is actually all vectors or quantities which are important for description of the magnetic field. But at the same time, these E and B remain, let's say, the main vectors, and these ones are just to help. What is actually vector E? What does it show? I can tell you what is the physical meaning of this electric field strength. The absolute value, the number of the electric field strength, actually tell you how much force acting on the charge of 1 coulomb placed inside of the electric field of certain strength. So we call the electric field of 1 volt per meter is such a field which acts on the particle with charge of 1 coulomb with force of 1 newton. And actually we didn't talk yet about where the force is acting. In electric field, force is usually acting along the field lines. And if we have positive charge, the force moving this charge towards the direction of the electric field. If we have negative, it moves to the negative direction. This is for electric field. I could also explain why volt per meter. It's actually very tricky mathematics behind, because 1 volt is joule by coulomb and newton by meter is actually joule. And from these two things, it can be stated that volt equals to newton meter by coulomb, or volt divided by meter, if we take meter from here to here, equals to newton by coulomb. So this is how these relations comes. So electric field can actually be measured in volt by meter or by newton by coulomb. And this is newton by coulomb is actually more physical explanation, because electric field in fact showing you how big force acting on the charge of 1 coulomb being placed in this field. So this comes from the physics, and this volt by meter comes from mathematics. What about magnetic field, which is more important for us in the context of electric machines? What is actually 1 Tesla? What it shows? It's actually very clearly comes from the decomposed value of Tesla. If we remember that 1 Tesla equals to Newton divided by ampere divided by meter. And definition of this quantitative value of magnetic field comes directly from the law of ampere, which is BIL for normal force. So if the magnetic field acting on the conductor, which goes in perpendicular direction to the field, we can use the ampere force equation. And what is actually magnetic field of 1 Tesla? This is magnetic field of such a strength that if we put the conductor with 1 ampere flowing inside of it, and this conductor has the length of 1 meter, then the force of 1 Newton acts on this conductor. So the definition comes from this equation. That's why we have this dimension Newton divided by ampere divided by meter, which for convenience named also as Tesla. That's actually all I wanted to tell you about the dimensions for electric and what is more important for magnetic fields. I hope now it's become a little bit more clear for you.